Thursday.
I know, yeah. Now this isn't in your booklet, and it really should have been, I think, done in the thermochemistry book. But I want to talk about reaction drivers. There are two. So enthalpy is a driver that you're all familiar with, aren't you? You know what enthalpy is, don't you? And we would, this drives us from high to low. So, if you like, an exothermic reaction is a natural reaction because we go from our reactants that have a lot of energy in the bonds to products that have less energy. So we're going from high energy to low energy. And we can think of that as energy as well. Okay. So you're already familiar with that one. And so, question then is, why then do endothermic reactions occur? If this is the natural driver that's higher energy to lower energy, then how can you possibly have an endothermic reaction? And the reason is that there's another driver. And the other driver is called entropy. And this is a very important part of the laws of thermodynamics. And this is a driver that drives from order to disorder. And it makes sense that this is a natural driver as well, because how hard is it to keep your room tidy? Okay, things are always becoming more jumbled up naturally. Things don't just sort of organise themselves quite easily. But what does that mean in the context of chemistry? Well, disorder could mean more particles. In which case we could look at the mole ratio of reactants to products. Are we breaking things apart so that we've got more parts for our products? If that's the case, then entropy will be driving the forward reaction. Sometimes there'll be equal numbers, like the mole ratio will be equal on either side, and so it won't be more particles. But to say they're more energetic, for example, a solid to liquid to gas, or to solid to gas, entropy is going to drive these in this direction. Because we know that our gaseous molecules are high energy, and they're going to move around, and they're much more disordered than a solid. Does that sort of make sense? So sometimes you might be asked to look at a reaction, and for those of you who've started looking at Criterion 6 questions in past exams, it might, if it uses this word drivers, that's a clue that it's asking you to look at the relationship between enthalpy and entropy. If it's an endothermic reaction, then entropy has won. Okay, if it's a battle between them, if one is driving the forward reaction and the other is driving the reverse reaction, we can see who wins by the value for the delta H. So sometimes they'll both drive in the same direction. That's pretty straightforward. In which case that's going to be an exothermic reaction, isn't it? but because we know that enthalpy really is always going to be driving to lower energy, to have an endothermic reaction, entropy has to be entropy must be winning. Okay, so we just needed to slot that in somewhere. Any questions about our reaction drivers?
Is entropy a measure of energy the same as enthalpy, or is it measured some other way?
We don't look at the true meaning of entropy, because this is, if you like, I'm only cut a slice off entropy, and this is all we need to worry about for chemistry. Yes, because you can calculate, but we don't do that. And look, it's a good thing. How would you feel at this time of year if we just bunged in another calculation for you to do to figure out which one's going to drive? But yes, we can quantify it. Any other questions about entropy? It is a word you need to memorise, I guess. Basically, you need to have them as part of your terminology that you are familiar with and can use. Okay, so I'll just stop the recording there. No more questions?